we present MATTopo, a volumetric restricted power diagram-based framework for computing the 3D medial axis while preserving topology, medial features, and geometry. Given an input 3D model, the approximation of the 3D medial axis aims to preserve the topology equivalence, medial features, and geometric convergence with respect to the input shape. This approximation also aims to be capable of handling various inputs, including organic models and CAD models. The topology equivalence is indicated by the Euler characteristic. Medial features include both external features, such as convex sharp edges and corners, shown in black, and internal features, which represent the inner structure of the shape, shown in red. The reconstructibility indicates the geometric accuracy of the approximated medial axis. Existing methods often consider these three properties as a trade-off. Classical methods struggle with topology correctness, such as power crust, PC, and the scaled axis transform, SAT, or require a large amount of medial spheres to preserve homotopy equivalents, such as voxel core, VC. Additionally, all of these methods perform poorly in terms of geometric convergence when approximating non-smooth CAD models with convex sharp edges and corners. MATTFP method has shown privileges in preserving medial features as well as geometric convergence for CAD models. However, it cannot guarantee the topological preservation as their experiments show inconsistency of the Euler characteristics. In this paper, we present a novel framework for computing a topology-preserving MAT that is homotopy equivalent to the input 3D shape. Our framework can also preserve medial features and ensure the geometric approximation accuracy. Our pipeline consists of 4 stages. The first stage is to generate initial medial mesh. Our method requires input that is a manifold tetrahedral mesh with single connected component and no cavity. The surface features such as sharp edges and corners are also pre-detected. The pipeline starts with an initial medial mesh of a small number of randomly placed medial spheres using the sphere shrinking algorithm. In this example, we generate 2 initial medial spheres. And we show the restricted power diagram, RPD, of this 2 medial spheres. In the second stage, we perform our topology preservation strategy. To ensure the homotopy equivalence, we are expecting 2 topological indicators of each restricted element of the RPD, all equals to 1. One indicator is the number of connected components, and another indicator is the Euler characteristic. For example, the restricted power cell, RPC, of this medial sphere, which locates on the top of the shape, has the number of connected components equals to 1. The Euler characteristic of this RPC also equals to 1. However, when it comes to checking the restricted power face, RPF, we observe that there are 2 connected components. Therefore, the topology test is not passed for the RPF, regardless of the Euler characteristic. If the test fails, we apply a straightforward refinement by adding new medial spheres in the local region. After adding a third medial sphere in this example, we can see that the homotopy equivalence is preserved with respect to the input shape. Here we perform the topology check again. The RPC passes the topology test as both indicators equal to 1. When it comes to checking the restricted power face, RPF, we can see that each of the RPF passes the topology check. Since this example contains no restricted power edge, RPE, our topology check would stop here. In the third stage, the medial features are preserved by checking if the RPCs of 2 adjacent medial spheres covers the same surface regions. We use the similar feature preservation strategies as MATTFP for preserving external features. If any sharp edge belongs to the cell of a non-feature sphere, new zero radius spheres will be added iteratively, as shown in blue. Similarly, internal features are preserved by inserting new internal feature spheres after detecting any deficiencies. For more detailed discussion, please refer to our paper. In the final stage, we propose an error-bounding strategy so that the geometric error from the input shape to the enveloping volume of medial mesh is bounded by a user-controlled threshold. Specifically, we use the distance from any surface sample X to its closest enveloping element as the metric. For each surface sample, we traverse all possible enveloping elements defined by the medial mesh and compute its distance to the closest enveloping element on the GPU. In this example, we show the closest element as the medial cone. If the ratio of the distance die over the diagonal of the bounding box is larger than a user-defined threshold, we insert a new medial sphere using the sphere shrinking algorithm. We show the center of generated medial spheres before and after the geometric preservation in red dots. Here we show some comparisons on both CAD model and organic model. We compare our method with 4 classical methods for approximating the 3D medial axis, including 3 point cloud-based methods and 1 voxel-based method. MATTopo and our method are the only 2 methods that takes medial feature preservation into account. All other methods struggle to preserve sharp edges and corners for CAD models. However, MATTopo struggles with topology preservation, as the Euler characteristic of its generated medial mesh is not consistent with the input shape. We also show the reconstructed meshes in light blue and the original shape in transparent. The best two-sided Hausdorff error is marked in green, and the second best is shown with underline. For the organic model with no clear sharp edges and corners, our method normally generates similar reconstruction accuracy with much fewer medial spheres. Our method can also maintain the topology and thinness property of the 3D medial axis. Here we show the reconstructed meshes and the color-coded distribution of two-sided Hausdorff errors between the input surface and the reconstructed surface. For more results and experiments, please refer to our paper. Thank you for watching.